Hello, everyone. My name is Languri, and it's my pleasure to be here with you. Quickly, I'm the Director of Industrial Training and Assessment Center. It's a U.S. Department of Energy funded program, and I'm also Associate Professor in the Department of Mechanical Engineering at Tennessee Tech University in Cookeville, Tennessee. So through the role of director in IAC. So it was initially Industrial Assessment Center, recently renamed to Industrial Training and Assessment Center. So if you hear IAC or ITAC, they're really the same. Through this role, I had the opportunity to be involved in energy assessments and cost saving and kind of doing sustainability improvement for various manufacturing facilities that I'm going to share some of those experience with you today. Before I start, I would like to acknowledge our former and current students, our staff at ITAC, Dr. Glenn Cunningham, our previous director of the center, Tennessee Tech University, that's supporting our really program, and our sponsor, U.S. Department of Energy, and ITAC program or IC program again, for the support they provided and they're doing. So let's get into the actual presentation. So I would like to start with U.S. energy consumption kind of flow chart that every year Lawrence Livermore National Lab provides. So on the left-hand side, you see all the sources of energy. You see petroleum is a major source, natural gas another major source. Still we have a lot of coal. We have some renewables, biomass, and on the right-hand side you see different sectors that they're using those energy. So residential, commercial, industrial, this is what we're focusing mostly today, and transportation. Quickly here, some of those fuels are getting converted to electricity in power plants, and so there are inefficiencies or losses going to rejected energy, and the useful electricity come to those different sectors. So if we just focus on industrial for now, we can see that out of 26.1 unit that comes into industrial sector, a little bit over half is getting rejected as a form of rejected energy, and really a useful energy is a little bit less than half. And of course, I'm going to highlight again that there are more rejection, there are more inefficiencies when we're doing electrification at the power plants to convert those fuels to electricity. So what we are today, what we're trying to do today here is that to work together to identify ways to reduce the rejected energy and add more to the net energy, useful energy you could use. And quickly, rejected energy or wasted energy or inefficiency is nothing but steam or hot water pipe that doesn't have insulation and reduces and basically reject the heat out. So you touch the insulation or bare pipe, it's hot. So this energy should be inside the pipe, go for really for a major purpose. Now it's wasted. So that's an example of what we're trying to do to kind of use the actual energy mostly in the useful way. Quickly, I picked beer industry to see their economic impact and to talk about what kind of really business we're looking at. Just looking at the breweries in Tennessee, I was really excited to see that there's a major total economic impact, $6.3 billion just by this sector itself. And of course, it's in charge of job creation and workforce really in various sectors, manufacturing jobs and really other jobs. And really what we're trying to do today is that if we can save the cost for a brewery or other industry sectors today by a few percent, roughly, I'm going to show we are covering 20% or more of the utility costs. And so the facility, you guys can use this cost saving into your productivity improvement. So this can impact this really already big kind of business in Tennessee we have. When I was doing more literature review, this information was interesting to me, that if you just break down the electricity use in brewery sector, you will see that a little bit over 45% of electricity is just used in the motors. And electric motors can be seen in compressor systems, in fans, in pumps, so anything that basically use the electric motors to do a job. Another good part is process cooling and heating, which is different than HVAC for air conditioning of the space. That has another major part, and others are lighting, HVAC as well. And you can see here this a small piece for steam and hot water, but I just want to highlight that this is just electric steam or hot water. So the steam, natural gas use is already big. It's a little bit outdated data, but we have more data to cover this. A little bit about IAC or ITAC, as I mentioned, Industrial Training and Assessment Center, founded back in 1976 with 4 universities at the time. And of course, right now we have 39 centers across the nation. Tennessee Tech University is the IAC in Tennessee. University of Memphis works with us as a satellite center. We are funded to do 20 energy assessments for various facilities in Tennessee and around Tennessee, mostly in Tennessee. And of course, there are other similar centers, but really very independent in nature. They're doing the same thing in their region. So Tennessee Tech IEC, particularly for us in Cookeville, Tennessee, we were established back in 2007. 2 goals at the time, and currently provide free, no-cost energy assessments to manufacturing, you guys, facilities, as well as training our students and training the workforce in the current business already. So this is how we look like. We are from 1 to 2 faculty members usually, and several students. Of course, these students, a lot of them are very experienced. They've done maybe over 50 energy assessments or so, and some of them, of course, are new. And we've worked with different sectors, utility representative or TVA. We show up at the plant. We're trying to help them how they can maximize the incentives in terms of utilities, in terms of energy audit, cost saving, and more. So we spend 1 day in the plant, in some cases 2 days, depending on the size. And we are giving them a full detailed report that shows all the details of the calculation, and then cost saving, payback period, and basically tools to make decision making easier. More on IEC, we have done 322 assessments so far. We track number of recommendations we do, amount of energy saving, and cost saving over there per each assessment, and of course, number of students we trained in this program. These dots represent assessments done in and around Tennessee. After 9 months, we do the assessment. We contact the facility again and say, hey, out of maybe 10 recommendations we had, how many have been implemented, and we collect those data. So the 9-month implementation survey shows us, in average, we have a little bit over 43% of our recommendations have been implemented. So for every 10 recommendations, 4 to 5 are being implemented in the year 1, roughly. So let's dive into more technical stuff on why we are here to really discuss energy saving in distilleries, wineries, and breweries. I was looking at the database we have for our IC, ITAC, and basically trying to understand what kind of recommendations we have done so far in these sectors. If you look at their NAICS code, that breweries, wineries, and distilleries, really the topic of this talk today, they have these codes, And you can see on the right-hand side at the ITAC program nationwide, they've done 71 energy assessments for breweries, 61 for wineries, 13 for distilleries. And Tennessee Tech, we had our portion as well. And of course, we have those recommendations as well. As I click in the database, you can go down to the details, a little bit more details of each recommendation. Of course, as earlier discussed, no information of any plant or a way to can map and connect each kind of recommendation to a plan is not available. It's not there. So everything is basically protected in a way that no data from the plan will be shared, but people can see for such a sector what kind of recommendations has been done without any details about the plant. And these are cost savings. So you can see that the amount of recommended saving per each sector is here. I work on the data a little bit more just to break it down. Out of 92 total assessment recommendations, just for the sector of distilleries, and I could do this for breweries and wineries, but really for this talk, I just did for distilleries. You can see that around 25% of the assessments recommended something for or related to compressed air system. So it can be anything around compressed air system. So that shows me that compressed air system is a major player in energy use, and of course provide major opportunities for cost saving in distilleries. Second and biggest one was the steam system. So anything with natural gas, usually or making high temperature, high pressure steam are expensive, so more opportunities. Lighting, HVAC, and utility. Of course, there are others as well, but if I'm gonna, as a program manager of a plant or as an engineer of the plant, if I'm gonna focus on, with my limited resources and time and budget, if I'm gonna focus on some areas to get the max saving out, I would start with compressed air, really those bigger items, steam systems and more. So I found this really interesting to see where are those big savings are. Let's go look at one of the energy assessments done in Tennessee really area. Again, this is for a distillery plant. You see some information about the plant, but very generic information. Over here you have this plant is running 24/7, 8760 hours per year. And here are some basic information about the plant. This plant was using wood to generate some steam as well as natural gas, but they're using some electricity as well. So the outcome of the assessment that you will see in that detailed report, if you do yours as well, imagine a 70-page report with a lot of details, but this is a bottom line, the table of the recommendations. So we had 5 recommendations for this plant. Number 1 was reduce combustion airflow to optimum. So this is more for steam system, for boiler, that could save them almost $90,000 with $25,000 cost with a 3-month payback period. So this is a no-brainer project. Reduce the steam pressure to generate power. So this is more on-site power generation using a Rankine cycle. So that would save you a little bit over $200K by generating some electricity with some cost, and installing a VFD drive, variable speed or variable frequency drive on some pumps, and reducing pressure of the compressed air system. So there's a compressed air recommendation as well, and of course lighting. And a lot of time these days, lightings are a project that's mostly done, but of course we see a lot of plants that still need lighting. But here is what it looks like that you will get out of such a report. This is actually a real case study that shows you the savings, the cost for doing the project, and the payback period, how many months it will pay for itself. Now that we know that compressed air system is the major one in terms of energy use in such a plant, let's go a little bit more deep into compressed air system, and let's identify some areas for energy optimization. And of course, energy optimization is nothing but cost saving in utility, or being more resilient, or really being more sustainable. So they're all interrelated. Compressed air system, as you can see in this picture, we can divide this into 4 major sections. Generation, which is nothing but your compressors. So here I'm showing 2 air compressors in such a plant. It can be run at the same time, or one redundant, or multiple compressor, or just one. Really, this is just a schematic. Then we have a section for conditioning, which is mostly filtering, separating oil from air, and drying. Those are the major part. We have a distribution system, those distributions, piping and headers, as well as the end users. Those users can be either a robot or any end users that kind of use it. And in each of those 4 sections, we can go deep and talk about how we can do things more energy efficient, which ends up saving costs and being more sustainable. But for today's talk, probably I'm going to cover a few of those, but really each of those can go really deep, and in some of the workshops we do and training we do, we go deep into each section. Starting with compression efficiency. So here I'm just showing an electric motor that is tied to a compressor, and the goal is to compress the molecules of the air so that we can have the air at a higher pressure. As you compress those molecules, it causes more friction, so there's a heat because of such a friction, and you have to reject the heat out of the compression process. So you can have a compressed air at the normal temperature, right? So out of 100 kW, let's assume you're putting 100 kW energy, power in this case, into this motor. You have some losses for energy losses. Let's assume 8 kW getting lost, and around 80 kW, almost 80%, 80 kW out of 100 kW inlet is rejected in the form of thermal energy, just because of those compression process. So really, useful energy leaving as a compressed air is very small amount, so 10 to 20% in this case. So just want to highlight that compression is not an efficient. Of course, compressed air is a very useful utility to have in the plant, and in each plant we go air compressed, or they're used by robots, by process, but just know that this is very inefficient. So there are a lot of ways to kind of improve the efficiency. One way can be reuse this waste heat, this 80%. So quickly, I'm going to start with saying that the hot air from those compressors can be ducted into the plant and used over the winter time. It's a very clean air, basically air from outside the room getting into the air compressor through the filters, and basically are rejected usually outside to the plant or left in the plant. So the ideal scenario would be can be ducted into the plant close to the nearest space that could heat the space in the winter time. Of course, in the summertime, you close this damper and you send everything outside. So that's one way to save energy. For compressed air, as we go further deep into the discussion, you need to measure things in order to manage it. So you can't manage what you don't measure. Here I'm showing some of the equipment we have been using in IEC that help us to identify where are the areas for energy efficiency improvement. Ideally, you're going to measure the compressed airflow. We don't see this a lot, really. We usually don't have airflow measurement unless you're using our ultrasonic coulometer on the pipe. But in some cases, very sophisticated compressed air system, you see there's the inline airflow, which is really useful. Steam pressure, so these are kind of pressure sensors that can go on the line and measure the pressure constantly. So these are you seeing on the right-hand side, are data loggers that can measure the current as well as pressure, maybe every second or every 5 seconds, depending on your setting of the plant. So this way, you can leave this for a week or two, or if this is owned by you, you can leave it constantly, and you have a good trend of data, how pressure and current, they behave over time during the weekdays, during break time, during weekends, during transitions. And that would be giving you a lot of data to understand where are opportunities to reduce the cost. Back to our list here, compressed power use. Those are these CT current transducers can help us. Ultrasonic leak detector, that's one major source leaks are that you can identify those. We're going to talk about it more today. Dryer pressure loss and filter pressure loss. So a lot of times those filter gauges are not working, filters are not replaced on time, so there's a major drop in pressure of the compressor just because of a bad filters or something clogged in the line. So we have seen so many of those that pressure setting of the compressor is very high, maybe 125, but the plant all needs is 90 psi, and really the reason when you spend the time to find it is not because you're really needing 125 psi in the plant, but because we have a major pressure drop somewhere in the line that is not expected and you couldn't identify it. And this multimeter here as well, we have the capability to measure the power factor for each equipment. Today we don't go deep into power factor discussion, but if an electric motor, in this case compressor, has a poor power factor, then you are penalized. Maybe if you're in a TVA region, a lot of time it's 85%. If you're below 85% power factor, you get penalized because of that, and there are ways to fix those. So this measurement can help you to identify if this machine caused you a power factor penalty or not, or regular, or in general each equipment. So we have, of course, access to these equipment and more than this, but and these are not very expensive. I have a picture of those here to show you maybe in the long run, you may want to invest on some of those current transducers or pressure loggers. This is the data logger that 4 channels are connected to this. And you can track those critical equipment that you can imagine those as a significant energy users, the way SEU, the way in 50,001 ready, we talked about it. You can get a lot of information from motor nameplate in a compressor or an electric motor and try to identify, so use the power equation to see what's the current it takes. So by reading a name tag, a lot of time we ignore this, but if you go deep into this, you get a lot of useful information. I quickly talked about it. We have 450 horsepower. This is the rotation per minute, volt and amp, power factor, nominal power factor, and NEMA efficiency. And you can kind of measure the power by multiplying current times voltage, some the square root of 3 because of the 3-phase, times power factor times efficiency divided by 746 to get that power. Just look at the time. I think I have a few more minutes to go. Then you use those power, when you use your current transducers and pressure sensors, you can create a profile like this. So the red one is pressure. You can read it on this axis. And remaining are current transducers that you can read on this amp. And you can see that if you have a multiple compressors, some of them are base loading for you, in this case the black one and green one, and some of them doing the trimming for you, providing those little air as needed. So in this case, this looks like a load-unload machine. And maybe this is also trimming while it almost looks like base loading as well. So really this helps us as you zoom in and you study this, or do we have enough storage in the plant to compress air? If we don't have enough storage, we see a lot of quick back and forth load unload here. Maybe with some storage we get a longer buffer as we have a larger storage, so our load unload doesn't work as hard. Or do we have a good control mechanism to have number of machines as a base load and one maybe only the best one for our trimming? Maybe the best one could be a VFD machine, not the load unload one, and everything else. So this gives us a lot of information to really talk about our pressure, especially what happened at different time of the day when we have a peak and we have a low in pressure. On this graph, I'm showing various control systems. So vertical axis shows you the power use out of 100%. Horizontal axis show you the capacity or CFM that your machine can produce and where you are in percentage of capacity. Quickly, I just want to highlight that in this limited time, that if you're at 40% capacity of CFM in your machine, if you're at the modulation control, which is not a very efficient way to control, you are using 80% of your maximum power to provide that 40%. But for the same size motor, if you are with the VFD, variable speed drive machine, or VSD, because of the better control, you are only using 40%. So there's a 40% energy saving right by switching from modulation to VSD. So these are helping us to kind of quantify what are the saving potentials depending on your control system. This is the equipment that kind of shows you the leaks for compressed air system. And so we use this tool and walk around the plant. This is the ultrasonic leak detector that show you the location and really the magnitude in decibel of the compressed air leak, that we can convert it to CFM and cost amount. But here I'm showing a simple table to show that for a leak, for a compressed air leak, if you know the orifice size at plant pressure, there are ways to approximate the cost of the air leak. And when you see the cost, $11,000 per year, just because of a small hole on a maybe a PRV or a line, that now maybe attract the attention, and now there's a plan to fix it. So compressed air leaks may not look big, but really when we put the dollar amount in, it can be a big number. I'm going to keep going, but if I'm getting around the time to stop, feel free, Caleb and Mark, to stop me. I don't mind. So there are other ways to estimate the leak load as well. So this is if your plant doesn't operate in a weekend, probably on a Sunday, this is a good way to exactly track your data to see what part of your compressor running loaded and what part unloaded, and kind of we go from there. This is the equation to quantify the leak really in the entire plant. Either you were able to see it with your leak detector or not, so that gives you an idea of what percent, maybe 50% of your compressed air CFM is just going to leak. So now you may want to really have a leak team to investigate where the leaks are and fix it. And of course, this is a continuing process. We are at 10:50. I think we started at 10, correct, yes. So I'm going to skip the steam systems for now. Mark
We'll give
and
you about
Caleb,
4 more minutes, and then we'll do
4 more minutes?
Q&A.
Okay, sounds good. I'm going to leave 2 minutes for a steam and 2 minutes at the end. I have a few things to share. So steam systems are second major part in your plants, really. So here we are showing a boiler, but boiler is only one section of the steam systems. And you may have some power generation, some turbines here, some users, some traps to extract the liquid out of the steam. And you have the aerator to get the oxygen out. You have a condensate receiver tank. You're collecting all those condensate back as much as you can. You have a water treatment and makeup water coming here, and your feed water going back into the boiler. When you are going at a plant, if you measure your exhaust flue at 450 and you measure the flue gas oxygen, this is the flue gas, this is the flue leaving the plant, leaving the stack. At 7%, your steam is at 700 Fahrenheit, and your fuel cost is 13 million. That's the cost of natural gas to run your boiler a year. Do you see an energy saving opportunity here? So first of all, we should know a way to measure our temperature of flue gas. In a lot of cases we do, but a lot of plants we go, they don't know about their oxygen content. So what's the oxygen content in the flue gas, not at the beginning, leaving the plant? So 7%. Is this too much? Is this good? So a stack loss is the highest loss in the steam system. So number one place to go and spend the time to try to improve is that just a stack loss reduction. Can we improve can we add the oxygen sensor? And I'll explain more later if I get the time to show the impact of this. And can we reuse some of this really high temperature heat leaving in some application? So for high temperature, can we use an economizer to preheat our feed water? And this way, our flue gas leaving at the lower temperature, and we use the waste heat in a good way to improve the efficiency of the system, because now we have a warmer feed water into the system or warmer air into the boiler. For 7% of flue gas oxygen, anywhere from 3 to 5% gives us enough oxygen that we are above a stoichiometric amount of oxygen we need, and each fuel molecule find the molecules of oxygen to have the combustion. So we can tune the burner to reduce the oxygen leaving the flue gas that's not really involved in the combustion back to ideally 3%, but anywhere from 3 to 5%. And this way we are showing saving. Here I'm showing one of our flue gas combustion analyzer inserted in the stack to measure the information we are looking. Maybe this will be my last slide on steam, that there are tools out there. I'm showing one table because it's simple to show a table rather than a software here. If you know the exhaust temperature of the flue gas, 450, ambient temperature, 70, then if you subtract 450 minus from 70 or 70 from 450, you get 380 temperature difference. And if you know your oxygen content in your flue gas, now you know that 21% of your energy is lost in the stack. So your efficiency of the system is 78%. So now we can talk about how we can improve it and gain the efficiency. Unfortunately, I don't have the time to cover this, but this is from a good source, Energy Star, on what are out there for you as a checklist to go and really invest the time, try to identify for energy savings and what's the average of payback period. I'm going to skip the details of this. These are softwares for us to use. Most of them are free of charge, except this app, I believe, that we can talk about. I guess this is my last slide, that IAC has an implementation grant that can cover up to $300,000 per manufacturing doing energy assessment. This is a federal grant. I don't know, with all the news and changes, recent changes. We had a meeting yesterday with our program managers, and still this grant, as I speak right now, is out there expecting receiving applications. The chance to win those are very high. So one of the requirements for this application for this grant is that the plan should have done an IAC assessment, so assessments done by one of our centers or equivalent one of our centers to apply for this plan. So a lot of our former clients applied to these grants and already received it and really implemented grant. The next quarterly review cycle is on April 1st. Again, this is still out there, and this is really helping manufacturers implementing some of the major energy projects for their plan. So it's very attractive and helping the industry. So hopefully we can see this continuing even after this deadline. With that, I'm going to stop here, and thank you so much for your time listening to this. I skipped a few slides, unfortunately, but I'm here to answer any questions you might have.
Thanks, Ethan. And yeah, just so everyone knows, these slides and the recording will be sent out with a follow-up, so we can dive deeper into some of those slides that we had to go through quickly. And of course, Dr. Languri has his email and his contact information here. I know that he would be happy to answer any questions that you might have moving forward. I had 2 questions come in, so I want to be cognizant of the time here, but I think they're good questions. Number 1 is, what is required to have an energy assessment for a producer?
Yes, any small and medium-sized manufacturing facilities, anyone with a utility cost a year less than 3.5 million, or number of employees less than 500 are eligible to contact us and apply. Even if you are larger than 3.5 or larger than that number of employees, we usually get approval. So we've done assessment for a larger plants like a $7 million utility. We can do those once or twice or more a year. But as long as you are a small and medium size, this is a free program for you to use.
And I'm going to save the last question. I want to go ahead and go over to our Mentimeter questions to capture the learning that was done here. So if everyone can pull their phones back out, we are going to go back over to our Mentimeter question. And if you don't have that pulled up still, just we have the QR code right there for you. Scan that for us, and then it'll bring you back in. Once again, asking those same 3 questions. How strongly do you feel that after a result of this webinar that you feel more knowledgeable about these topics? So hopefully this will show that there was some learning done. I know I've done work with ITAC's IAC. I've actually been able to go out and do a couple energy assessments within some manufacturers, and I feel like every time that I hear Dr. Languri speak, I learn more about opportunities to reduce energy use and be more efficient with your energy, and then also just the amazing things that their organization does. So appreciate everybody voting or completing the survey for us. And then I want to, so I'll keep this on, so if you're still trying to figure out which one you want to choose, go for it and keep doing that. I'm not going to turn it off, but I do want to go back to here to give Dr. Languri's contact information for you, and then also I have one more question that came in, and that is, are there any general low-hanging fruit that you commonly find for spirit producers? I know that at the very beginning you mentioned compressed air, but didn't know if off the top of your head you could think of for the spirit producers low-hanging fruit that they could work on.
Sure. I would quickly mention lighting. If lighting is not converted to LED, is a really no-brainer. Steam compressed air leaks, that is major energy waste, really cost-saving, and really anything around natural gas around a steam system, around compressed air system, around HVAC are having a very quick payback period, again, in terms of cost saving and being able to pay you back within 2 years are really good. I think, yeah, those are the things. And of course, one of the slides that I have is some details that I skipped. Those gives you a good idea about some ideas about the opportunities and payback periods. So I would follow that list as well.
Awesome. Well, thank you so much. Mark, thank you for giving us a rundown of the Tennessee Sustainable Spirits Program. If you're out there and you are interested or you know of a facility that would be a good addition to our program, feel free to reach out to us, myself or Mark, and then also Dr. Languri, thank you so much for all the work that you do for our industry and for our environment. We really appreciate, I always appreciate getting to work with you and learn from you. So like I mentioned before, the recording of this and the slides will be sent out as a follow-up. If you have, if you're sitting at dinner tonight and you're like, oh man, I wish I would have asked Dr. Languri about X, feel free to shoot us an email. You have his contact information, you have our contact information. Shoot us an email where we can work on getting your questions answered. And we really appreciate everyone registering and for being a part of this year's first Tennessee Sustainable Spirits webinar.